Your body is a city of over 30 trillion citizens, and just like in any city, there are rules. Work together, respect boundaries, know when it's time to retire. For a lifetime, trillions of your cells follow these rules flawlessly. But what happens when a few of them decide to rebel? What happens when a cell forgets who it is and begins a hostile takeover from within? Today, we're going on a journey deep inside the body to witness the birth of a tumor and to see the incredible microscopic war your body wages every single day to keep you safe. This isn't a story of fear, it's a story of resilience, control, and the hidden power of your own biology. To understand how a cell goes rogue, we first need to appreciate the perfection of a normal one. Inside the nucleus of almost every cell in your body is your DNA, a magnificent spiraling instruction manual over 3 billion letters long. This manual contains the blueprints for everything the cell does, including the most important rule of all, when to divide and when to stop. This process, called the cell cycle, is controlled by specific genes. Think of it like driving a car. You have genes called proto-oncogenes, which act as the accelerator, telling the cell to grow and divide, and you have tumor suppressor genes, which are the brakes, telling the cell to slow down, repair mistakes, or even self-destruct if it's too damaged. In a healthy body, this balance of accelerator and brakes works in perfect harmony, ensuring tissues are repaired and replaced in an orderly fashion. But our DNA isn't written in stone. It's constantly being copied, and with billions of letters to replicate, sometimes mistakes happen. A letter might get swapped, deleted, or inserted incorrectly. This is called a mutation. These mutations can occur as a simple random error during cell division, or they can be caused by external factors, known as carcinogens, such as radiation from the sun or chemicals in tobacco smoke. Now your body anticipates this. It has an incredible squad of proteins and enzymes that act as proofreaders and mechanics. They constantly patrol the DNA, finding and fixing the vast majority of these errors almost as soon as they happen. Most of the time, this repair system is so efficient that the mutation is corrected without any consequence, and the cell continues on its normal healthy path. The problem begins when a mutation slips past these repair crews, and it happens to strike a critical gene. Imagine a mutation damaging a tumor suppressor gene. The cell's brakes. Now the braking system might be a little weaker. The cell might not stop at a checkpoint when it should. Or imagine a mutation hitting a proto-oncogene, turning it into what's called an oncogene. This is like the car's accelerator getting stuck down. The cell now receives a constant internal signal to grow and divide, whether the body needs it to or not. Crucially, a single mutation is almost never enough to cause a major problem. A cell with faulty brakes might still have a functional steering wheel and other safety systems. True trouble arises when, over months or years, that same cell line accumulates more mutations, knocking out multiple safety systems one by one in a dangerous snowball effect. After accumulating several of these critical mutations, a cell may finally cross a line. It sheds its identity as a cooperative member of its tissue and becomes a renegade. It ignores the frantic signals from its neighbors telling it to stop. It becomes deaf to the internal commands telling it to self-destruct for the greater good. Instead, its new, corrupted DNA has only one instruction left: divide. And so it does. It splits into 2, then 4, then 8, creating clones of itself that all share the same genetic defects and the same rebellious drive. This small but growing cluster of abnormal cells is the very beginning of a tumor. It's a tiny, localized insurrection, a pocket of chaos in an otherwise orderly system. At this stage, it is still microscopic, but it is a seed of disorder. But the body does not stand by idly. It has a masterful surveillance system, the immune system. The first line of defense is the innate immune system, and its elite soldiers are the natural killer cells, or NK cells. Think of them as patrol officers walking the beat in your cellular city. They don't need a warrant or prior intelligence to act. NK cells are uniquely skilled at recognizing signs of stress or abnormality on the surface of other cells. When a cell becomes cancerous, its surface changes, displaying unusual proteins or missing normal ones. The NK cell bumps into this rogue cell, recognizes it as a threat, and latches on. It then releases powerful granules that punch holes in the rogue cell's membrane and order it to undergo apoptosis, a clean, programmed self-destruction. In many cases, this is where the story ends. The NK cells eliminate the threat before it can even become a detectable tumor. If the renegade cells divide too quickly and begin to overwhelm the NK cells, the body calls for backup. It activates the adaptive immune system, a more specialized and powerful branch of defense. This process starts with cells called antigen-presenting cells, or APCs, acting like crime scene investigators. They find a rogue cell, engulf it, and break it down. Then they take a piece of the abnormal protein from inside, a fragment called an antigen, and display it on their own surface. This is the evidence. The APC then travels from the site of the insurrection through the lymphatic system to a nearby lymph node, which acts as the immune system's command center. Here, it will present this evidence to the most highly trained specialists in the entire immune army. Inside the lymph node, the APC seeks out a specific type of T cell, a powerful white blood cell that happens to have the exact receptor to match the antigen being presented. This is like finding the one detective who recognizes the suspect's face. Once a match is found, a massive mobilization begins. The T cell is activated, and with the help of other helper T cells, it begins to clone itself by the thousands, creating an entire army of cytotoxic T cells all programmed with a single mission: to hunt down and destroy any cell in the body displaying that specific piece of evidence. These specialized T cells are then released from the lymph node into the bloodstream. They are relentless, targeted assassins that circulate throughout the entire body, seeking out the tumor cells and leaving healthy cells completely unharmed. However, the battle is not always one-sided. Just as the immune system is adapting to fight the tumor is adapting to survive the immune system. We now know this process is called immunoediting. Some tumor cells, through sheer random mutation, may stumble upon ways to evade the immune attack. For example, a cancer cell might stop displaying the abnormal antigen on its surface, effectively becoming invisible to the T cells that are hunting it. Other tumor cells learn to produce chemical signals that act like a white flag, tricking the T cells into thinking they are friendly. Some can even release substances that exhaust the immune cells, shutting down the attack completely. It is this complex, dynamic dance between the immune system's attack and the tumor's evasion that often determines the outcome of this internal conflict. This ongoing battle helps us understand a crucial distinction: the difference between a benign and a malignant tumor. A benign tumor is one where the rogue cells are still somewhat contained. They multiply, but they respect tissue boundaries. They are typically enclosed in a fibrous capsule. Like a rebellion that has been successfully quarantined to a single city block, it can still cause problems by pressing on nearby organs, but it doesn't invade them or spread. A malignant tumor, which is what we call cancer, is different. These cells have accumulated mutations that allow them to be invasive. They can dissolve the barriers that contain them, infiltrate surrounding tissues, and even orchestrate the growth of new blood vessels to supply themselves with nutrients, a process called angiogenesis. From there, they can enter the bloodstream or lymphatic system and travel to distant parts of the body to form new tumors, a spread known as metastasis. This incredible internal war highlights just how resilient and protective our bodies are. While we can't control every single cell division, we can take steps to support our body's amazing defense systems. A balanced diet rich in vitamins and antioxidants, regular physical activity, and adequate sleep all contribute to a robust and responsive immune system. Furthermore, avoiding known carcinogens like tobacco and excessive sun exposure reduces the number of initial mutations that your body has to deal with in the first place. Understanding this intricate process isn't about worrying about what could go wrong. It's about marveling at what your body does right every second of every day, and empowering ourselves to be active partners in our own health. Your body is a testament to balance, order, and incredible defense. From the DNA repair crews to the intelligence of the T cells, you are protected by a system of breathtaking complexity. If you found this journey into the cellular world fascinating, subscribe to the channel for more content explaining the wonders of your body. And to take your health knowledge to the next level, download our dedicated app, which you can find in the description and in our bio. Thank you for watching.